So let's take a look now at a function and see if we can't figure out analytically, without having to graph it, where its horizontal asymptotes are. And so let's look at the function f of x equal to 2x squared plus 3 divided by x squared minus 4x. So I've got a lot of things going on here. Now, if I want to find the horizontal asymptotes, then what I really want to do is I want to find the limit as x approaches infinity of this function f of x. So if it asks you to find the horizontal asymptotes, this is the mechanism that you want to create. Now then, I have kind of an issue here. As x grows infinitely large, the numerator is growing infinitely large, the denominator is growing infinitely large. I get kind of this idea of infinity over infinity, which is actually an indeterminate form, very similar to what we saw with 0 over 0 earlier in this unit. And so that means that I need to do something else. So here's the trick to finding horizontal asymptotes. To find the value of a horizontal asymptote, and I'm going to do this trick once, and then we're going to kind of get an idea, an intuitive idea when we analyze functions here. But to find the value of this horizontal asymptote, what we want to do is we want to divide each term by the highest power of x in the denominator. And then we want to take the limit, and we're going to invoke some of the algebraic properties of limits that we've learned in this class. So we're going to divide by the highest power of x in the denominator, and then see what happens when we take the limit as x approaches infinity. And we're going to use some of those fundamental ideas that we came up with in the previous video. So if I look at my function here, my highest power of x in the denominator is x squared. And so what I'm going to do is I'm going to divide every single term by x squared. Another way to think about it would be to multiply by 1 over x squared over 1 over x squared, which I can do because that's a form of 1. And when I do that, the limit as x approaches infinity, so I have 2x squared over x squared plus 3 over x squared divided by x squared over x squared minus 4x over x squared. And you might look at that and say, there is no way that you've made that simpler on yourself. But in reality, I have, because now I can do some simplification. Let's simplify each term as much as we can. 2x squared over x squared is 2. 3 over x squared is just 3 over x squared, but that's okay. Divided by x squared over x squared, which is 1. 4x over x squared is going to behave as 4 over x. Now, I don't want to have to write this next statement out, although we really could. We know from our algebraic properties of limits that I can evaluate this limit by looking at each individual piece. And so I'm going to do that here. The limit as x approaches infinity of 2, well, for any constant, the limit is just that constant, that's 2. The limit as x approaches infinity of 3 over x squared, this is kind of a corollary to what we saw in the previous video. As x is growing infinitely large, even though it's 3 instead of 1, the 3 really doesn't, it loses control of this function really fast. 3 divided by something really infinitely large is headed to 0. Limit as x approaches infinity of this constant 1 is 1. 4 over x, same thing with the 4. It's getting divided by something that's growing infinitely large. That's also headed to 0. And so this ends up equaling 2. And you can see that this trick, even though it made it look ugly at first, it actually created a very easy evaluation of this limit to say that it equals 2. So I can now say f of x has a horizontal asymptote at the line y equals 2. And what we kind of can see here, and you can kind of envision this happening to any other functions, really if you think about as x is growing infinitely large here, does the 3 really mean much? I mean, if you start thinking about 100 being squared and then doubled and then adding 3, then you start doing it with 1,000 and then 1,000,000. The fact of the matter is this plus 3 has very little impact, especially the further we go down the number line on what's happening on this function. Now, even though we have a 4x right here, it has the same idea. What is driving this function are the highest powers of x, 2x squared and x squared. And if you can see that, you can see where this 2 comes from. And so what we really want to say to make things a little more efficient on ourselves, and I'll tell you this process right here always works, but it is kind of nice to be able to say that the end behavior of graphs is really dictated by the largest powers of x in both the numerator and the denominator. And so when you're evaluating these limits to determine where a horizontal asymptote is, you really can just focus on the highest powers of x in the numerator and in the denominator. So let's take a look at an example here. Let's take a look if we were evaluating the limit as x approaches infinity of 3x squared minus x minus 2 divided by 5x squared plus 4x plus 1. Again, as x is growing infinitely large, the thing that takes control is 3x squared and 5x squared. In fact, I can go ahead and make the claim that this is approximately equal to just simply the limit as x approaches infinity of 3x squared over 5x squared. Well, if I gave you that, the first thing you would tell me to do is to divide off the x squareds. So I can say the limit as x approaches infinity of 3/5, which is in fact that constant 3/5. And so making this little approximation, just kind of an algebra technique of understanding what's in control as x approaches infinity, gives me this result of 3/5. And so I can say that this particular function, which I didn't name, but I can say that the function has a horizontal asymptote at the horizontal line, which remember always begins y equals 3/5. Now on these previous two examples, I really needed to also address what happens as x approaches negative infinity. But if you look at what happens, whether I'm approaching positive infinity or negative infinity, I was headed to 3/5, and in this case I was headed to 2. In the next video, we'll look at some situations where we actually need to address what goes on at positive infinity and what goes on at negative infinity.